Welcome back to Bite Size MCAT. When learning SN1 versus SN2 versus E1 versus E2, most students memorize four separate reactions, but there's actually a decision tree that you can follow. By the end of this video, I hope you'll be able to determine which mechanisms predominate in under 10 seconds. This will be helpful for your organic chemistry courses, and some of the basics covered here apply to the MCAT as well. First, let's talk about two major players and some definitions here. The nucleophile is something that simply attacks a carbon. A nucleophile can be much more than that, but for the context of these reactions, a nucleophile attacks a carbon. Nucleophiles have high electron density and want to donate that density. Now, when I say attack, this means forming a bond with. So a nucleophile will form a bond with a carbon atom. Some examples include iodide, thiols, bromides, and chlorides. On the other hand, a base is something that attacks a proton and steals it from the substrate. As a review, this is a Bronsted-Lowry base. The base will form a bond with this proton, and some examples include DBU, hydroxide, and methoxide. Another definition we will need to know is a leaving group, which is simply an atom or molecule that detaches during a chemical reaction. So, overview, nucleophile attacks a carbon and bases attack protons. One thing to note is that something or some molecule can be both a strong base and a strong nucleophile, just one or the other, or weak in both categories. We will discuss more on this later. Now let's get into our two major types of reactions before we talk about the possible mechanisms. First, we have a substitution, in which a nucleophile replaces a leaving group. Here's an example of substitution where a chloride replaces a bromide leaving group. The second reaction we have is an elimination reaction, where a base, just imagine some base, removes a proton, and this, along with the loss of leaving group, forms a double bond. Now, this is an extremely simplistic overview, but it will give us a running head start as we move towards understanding mechanisms. SN2 is a little easier to break down, so we will start here. To break down what this means, let's just take a look at the names. The S stands for substitution. If we go back to our original definitions, we are substituting one group for another group. For example, the chloride is substituting the bromide. The second part is N, which stands for nucleophilic. Nucleophiles have high electron density, so they attack carbons that are electrophilic. In this example, this chloride is attacking and displacing this bromide. Lastly, this reaction is bimolecular. This means that there are two species involved. In this case, the rate is dependent on both the alkyl halide substrate and the nucleophile. In an SN2 reaction, the nucleophile attacks and the leaving group leaves at the same time. We call this being a concerted reaction, or they both happen at the same time. One impact of this is that there's an inversion of stereochemistry. If we look at the bromide, it's on a wedge, but now the chloride is dashed back. This is because the nucleophilic chloride has to attack from the backside of the bromide due to the steric hindrance. So, SN2, nucleophilic substitution reaction that is bimolecular. This is a concerted reaction where the nucleophile attacks and the leaving group leaves at the same time. This results in an inversion of stereochemistry. What about SN1? The first two parts are the same. This is a nucleophilic substitution reaction. But what changes now is that this is unimolecular, because it only involves the alkyl halide substrate. As a result, the rate is fully dependent on the stability of this leaving group. So let's take a look at this mechanism. The first thing that happens is the leaving group leaves, so this bromide just leaves. Then the chloride attacks the positive carbocation that is left behind and forms a bond. So first the leaving group leaves, then the nucleophile attacks. This is what we call a stepwise reaction. Because there are no backside attacks, the chloride can attack on either side of the carbocation. This forms a racemic mixture. So, SN1, nucleophilic substitution reaction that is unimolecular. This is a stepwise reaction where the leaving group leaves first, then the nucleophile attacks. This results in a racemic mixture. Let's move to talking about elimination reactions. Let's start with the bimolecular reaction first because it is easier. E2 is simply an elimination reaction that is bimolecular. Think back to SN2. Was it concerted or stepwise? That's right, it was a concerted reaction that was dependent on two things. Here it is dependent on both the substrate and now the base rather than the nucleophile. The mechanism to the right shows both the leaving group leaving and a proton transfer happening at the same time. This leaves us with a double bond. So there are stereochemical and regiochemical outcomes to discuss. In this video, I want to talk about the regiochemistry, but the stereochemical outcomes will be the topic for a separate video. So, overview. E2 is a bimolecular elimination reaction where there's a concerted loss of leaving group and proton transfer that forms a double bond. E1 is a unimolecular elimination reaction. Similar to SN1, being unimolecular means that the rate is dependent on the alkyl halide substrate. Think back again. Was SN1 concerted or stepwise? That's right, this time it was stepwise. The leaving group leaves first, and then a base comes to steal this proton. This stepwise reaction yields a double bond as well. So E1, unimolecular elimination reaction, it is stepwise with a loss of leaving group followed by a proton transfer. Here's a brief discussion on regiochemistry for elimination products. Again, we won't discuss stereochemistry in this video because I think it will just take too long, but know that it matters for some products. Remember how we had to consider either an inversion of stereochemistry or a racemic mixture for SN1 versus SN2? For elimination, we have to consider the regiochemistry, or where the double bond will actually end up. If we look at this bromide here, we can imagine a double bond forming to either the right or to the left of that bromide. This is because we could take a proton from either side, and we see those products over on the right. Now, we have specific names for these, named after scientists, on these two possible combinations. The more substituted product, we call this one the Zaitsev product. If we look at this double bond, we have 1, 2, 3 substituents, or I like to call it 3 friends, holding that double bond. The other product is less substituted, and we call that one the Hofmann product. If we look, this guy only has 1 substituent, or 1 friend. This first example is using a small base. Small bases like sodium methoxide, sodium hydroxide, sodium ethoxide favor the more substituted Zaitsev product. So this is a small base and favors Zaitsev. So in the real world, you would get a mixture of both of these, but generally your professors will ask you for the major product or have you specify which product is in greater quantity. So the Zaitsev is going to be the majority of our product, while the Hofmann is going to be the minority of the product. Now, if we wanted to create more of the Hofmann product, we would have to use a large, bulky base. My personal favorite is this t-butoxide. Here's a picture of it. If we look at this, it is far bulkier than sodium methoxide or ethoxide. This is a large, bulky base, and as a result, this cannot cram into the small space required to remove a proton for the more substituted side. As a result, it will favor the less substituted side due to the sterical region. If we use a bulky base like t-butoxide, TEA, or DBN, we will favor the Hofmann product. So the Hofmann product will be the majority, while the Zaitsev will be the minority. Let's start our workflow or our process. Step 1 is simply identifying the reagent. What is reacting with our substrate? This is going to be whatever reagent is listed on top of the chemical reaction arrow. Use this table to determine if a reagent is basic, nucleophilic, or both. For example, our highly negative atoms are generally nucleophilic, like our halides. Our molecules that have oxygen and are negative are generally both strong bases and strong nucleophiles. Look for the patterns in these groups, like strong bases, weak nucleophiles are kind of these odd ones out, or weak base, weak nucleophiles are protonated versions of strong base, strong nucleophiles. Strong prediction skills requires knowing your reagents. The second step is identifying the substitution of our substrate. Here are the 3 main substitutions that we have. Primary means that we only have 1 carbon attached to the carbon that has our leaving group. This means when our leaving group leaves, the carbon that it was attached to only has 1 friend. If this carbon has 2 friends, then we call it secondary, and if it has 3, then we call it tertiary. Step 3 involves using this table to predict the mechanism. So once we have identified our reagents and our substrate, now let's finally predict the mechanism. For example, if we have, let's say, a strong nucleophile, weak base, but we have a secondary substrate, then our product will follow an SN2 mechanism. Now, what happens if we have a strong base, weak nucleophile with a tertiary substrate? Then we have an E2 mechanism. Again, don't memorize this, but seek to understand it. If we have a strong base, we will have an elimination product of some sort. If we have a strong nucleophile, we will generally follow a substitution reaction. I want to talk about some of these special cases. Let's say we have a strong nucleophile, strong base. Our products mainly depend on our substrate. If we have a primary substrate, our major product will follow an SN2 mechanism, while our minor will follow an E2 mechanism. If we have a secondary substrate, this will flip, and our major product will follow an E2 mechanism, while our minor product will follow an SN2 mechanism. Another special case is if we're weak in both nucleophilicity and basicity. Literature differs on what will happen, but generally speaking, we will only have a reaction with a tertiary substrate. This will yield half SN1 and half E1 product. I just want to make a quick note that in real organic chemistry, solvent and temperature can ultimately influence the mechanism of the reaction. This is especially important when specifically looking at characteristics that will favor SN1 versus SN2. However, in most OChem courses, the reagent and substrate are sufficient in predicting the correct answer. Our last step is considering stereochemistry and regiochemistry. For SN2, we have an inversion of stereochemistry, and the nucleophile attaches where the leaving group leaves. SN1, we produce a racemic mixture, and the nucleophile attaches where the leaving group is unless there's some sort of carbocation rearrangement. For E2, stereochemistry will be left for another video, but for regiochemistry, this is wholly dependent on the base being used. Remember, a small base will favor the Zaitsev product, the more substituted, while a large bulky base will favor the Hofmann, the less substituted. Lastly, for E1, Zaitsev is almost always favored due to carbocation rearrangements. So now let's put it all together with two practice problems. I will make a separate video with more practice problems in the future, but let's start here. So what was our first step? Yeah, let's classify our reagent. Sodium methoxide functions as what? If we look back at the table, it's a strong nucleophile and a strong base. Now, what's our second step? Let's look at the substrate. Let's look at where this chloride is attached. Is it primary, secondary, or tertiary? Yeah, it's a primary substrate. With this, what is our mechanism? Looking back at the table, we find that SN2 predominates while E2 forms our minor product. Lastly, we have to remember that SN2 has an inversion of stereochemistry. In E2, we will have to deal with Zaitsev versus Hofmann. So let's start drawing. Our major product will substitute methoxide for the chloride. There is normally an inversion of stereochemistry, but because the carbon that the chloride was attached to was achiral, we do not have to worry about this here. What about our minor product? E2 eliminates the chloride and forms a double bond. Because we don't have any other places this double bond can be, we don't have to worry about Zaitsev or Hofmann, so we only have one E2 product. And that's our first example. Okay, now that we've done one together, pause the video here and try to solve this for yourself. Okay, let's work through it. Our reagent is DBU, right? So this is going to be a strong base, weak nucleophile. Our substrate is what? Yeah, it's tertiary, and together this leads us to predict an E2 reaction that predominates. So now, what do we have to consider for E2? Yeah, Zaitsev versus Hofmann. So is this a small or a big base? DBU is actually one of our large bases. So because this is a large base, we're going to favor our Hofmann product. So let's draw our answers now. Our major product is this Hofmann product, which places the double bond here. Our Zaitsev product is going to be this product over here and places the double bond here in the center. But this is going to be our minor product, even though it's more substituted. Great work, guys. So I hope in this video you learned a strong overview of substitution versus elimination reactions and how to predict the mechanism. Thanks for watching.